Our second talk of the afternoon session will be Dan Fried from UT Austin, talking about topological symmetry in field theory.
Well, thank you. It's an honor and a delight to be here to help celebrate Hiroshi's birthday. I've known and admired Hiroshi for many years, and I now have the pleasure of working with him on a hard, perhaps insoluble problem, and hopefully the first of many, many projects. But today I'm talking about something different. It's joint work with the two characters listed here. And you can find the paper that we recently put out, as well as some lecture notes, I think should be accessible from that website, a summer school course I gave this summer. So, so we're all part of this Simons collaboration. There are probably 18, I don't know, quite a number of us, mathematicians and physicists. And that started a year ago. And the summer before it started, the three of us decided we should try to figure out what this Simons collaboration is about, what this title means. And so what I'm going to tell you in rather elementary terms, I hope, is our thoughts about that. So symmetry in quantum field theory and quantum gravity is obviously a huge subject, and Hiroshi has made many, many important contributions to that. And what we're going to talk about today are internal symmetries, you might call internal topological symmetries in quantum field theory. And the point is that it will lead to a kind of calculus of topological defects that leverages the advances we've made in understanding topological field theory. So there's now quite a sophisticated development around topological field theory, and we can use those to make calculations. So I'm really going to explain, the whole talk is in the next few slides, but it's nothing to do with field theory. It's something just about matrices and Lie groups and Lie algebras. So here's a basis for the Lie algebra SL2R, the 2x2 traceless real matrices, these three matrices. And well, I think all of you could do in your heads this calculation of both sides of this identity. Just means matrix multiplication and matrix addition there. And you'll easily see that those two sides are equal. And in fact, it's the scalar matrix indicated below. So maybe I should point out that this is not a calculation in the Lie algebra of SL2. For example, the answer doesn't have trace 0. So this is in the algebra of matrices, the associative algebra of matrices that we're computing. Well, we could go to the three-dimensional representation, and here are those same three elements of SL2R. And now, maybe it would be a little harder to do in your head, but it's still true that that identity holds. And it's still true that you get a scalar matrix, although a different constant. Well, you might imagine the next slide is the 4x4 case, the 5x5, but we won't do that. But here's a different representation. So SL2R, really its quotient PSL2R, is the classic group of projective transformations of the projective line. Such a thing is illustrated if you were fortunate enough to study that kind of classical geometry, cross ratio. And if we look at the projective line, that's geometrically a circle, we could look at differentials on that with any complex power lambda, and that group will act by pullback. So by differentiating, so will the Lie algebra, and here's the action, if I computed it correctly, probably close, of these three basis elements. And so now we could look at our basic identity, where h squared now means the composition of this differential operator with itself. So we'll get second order operators, and we can do the identity again, and lo and behold, it's still true. The constant is again different, depends on lambda. So the calculations look very different in these three different manifestations or representations of the symmetry, but clearly there's just one calculation going on here. And that calculation takes place universally in an algebra. It's what's called the universal enveloping algebra of this Lie algebra. So it's the algebra you get by taking expressions on the three symbols E, F, and H, and simply imposing the relation that the commutator xy minus yx in the algebra equal the Lie bracket in the Lie algebra you started with. And so you see this identity viewed in this abstract algebra. This is an expression we get by addition and multiplication of these generators that identity follows very simply from just this calculation that EF minus FE is the commutator, that's the universal enveloping algebra, and that's equal to H in the Lie group. And that's it. And once you do that little computation, you know it has to hold in all these representations, even though in all those representations, the calculation looks different. That's the talk. Well, so there are a lot of papers in, especially the last few years, about symmetry, various forms and extensions and so on of symmetry in quantum field theory. And in the physics papers among these, I think you'll find a lot of calculations of the sort of the first three I showed you. In particular representations, there are some calculations about certain topological defects and so on. But the point of the talk is to show you a kind of universal place in which to make those calculations. So that's the main idea of the talk, is to make those calculations universally in quantum field theory, to show you a framework in which to do it. Okay, so the word symmetry, by the way, that I usually think of, I think of taking some mathematical object, maybe a geometric shape, and doing some transformation that preserves whatever properties we're studying. Well, of course, I can undo that transformation. I don't usually think of something that collapses as being a symmetry. So this phrase noninvertible symmetry is a rather harsh to my ear, I must say. But at the same breath, I would say that algebras of operators, where algebras have non-units, non-invertible elements, they date from the very beginnings of quantum mechanics, of course. Von Neumann developed theories of topological algebras, von Neumann algebras, C-star algebras, and so on, in the late 20s and early 30s, because he was thinking about quantum mechanics simultaneously. So it's not a new idea to have operators that are not invertible. Okay, so here's the picture of that we want to imitate in quantum field theory. So there's a notion of an abstract kind of data, and then its concrete realization, analogous to what we had before, or analogous to the idea of an abstract group versus some representation of the group, linear or nonlinear. So the abstract is a pair. It's an algebra A and the right regular module. So the right regular module is the vector space A with the action of A by right multiplication. So as a vector space, it's the same underlying vector space as A, but it has the structure of right multiplication. We're not remembering the algebra structure. And what does it mean for that to act on a vector space V? Well, it means that we give a left module, that's this L, so that A acts now on the left of L, and we give an isomorphism theta that says that if we make this what you might call a sandwich, we take the tensor product of the right and left module over the algebra A, so we use up the action of A, and what's left is a vector space. We don't have anything acting anymore. That has to be the vector space we started with. Well, in this example, that's a little bit precious, you might say, because you can look at the left module and say, well, there's an underlying vector space, that's the vector space V. But we'll see that in the quantum field theory context, the L, the left module, and the vector space might look very different. So that's what I just said, I think. Right, so the idea is that when you have this abstract algebra with its right module, you can study relations, as the one I wrote in the universal enveloping algebra of SL2R, and then that holds in every left module where it's acting. So in general, by the way, I tend to think of left actions as something geometric and right actions as something structural. So this right module is part of the structure of the algebra that we're using as part of the abstract symmetry, and the left action is the geometric one. So the analogy is that we're going to replace the algebra by a topological field theory, and the elements of the algebra that act as operators will be replaced by defects in the topological field theory. That's what will be acting on the field theory as these kind of symmetries, if you like. Okay, so let me say a word about how we think about field theory. And you could think about it as analogous to having a representation of a group, that a field theory should be some kind of, it's a quantum system, some kind of complex linear representation of something. And that analogy is limited, but useful in the big picture. So these are axioms that Graham-Siegel introduced in the mid to late 80s in the context of two-dimensional conformal field theory. Then Michael Atiyah took them over in topological field theory, pointed out the connection with Bordism theory and topology. And really, they should be thought of quite generally, I think, for field theory. So it's modeling a Wick-rotated field theory, and Wick-rotated and coupled to compact curved manifolds. So there are two kind of discrete parameters that tell you the type of the theory. One is the dimension of the theory, and the other one are the background fields. So in this definition, there are no fluctuating fields. They've already been dealt with. So what's left is the dependence on the background fields. In the same way, you wouldn't tell me we're studying representations of a three-dimensional Lie group, because that Lie group could be SU2, could be SL2R, could be the torus. You really need to tell both of these to tell what kind of theory you're talking about. And so in these axioms, you attach to a codimension 1 manifold that's closed a vector space. You should think of that as the vector space of states of the quantum mechanical system. And then if we have a transition between two of them, here we have these two components going in and this one going out. There's some topology change in the middle, but you might also imagine these background fields like a metric or conformal structure, what have you. Then what we get is a linear operator. So it's a representation of Bordism, taking this curve thing into something linear, just as a representation of a group does. So this is, of course, the most well-developed in the context of topology. And there's a version that's fully local, that has locality to the nth degree, where you're allowed not just to cut this n manifold in codimension 1, but you can cut in codimension 2, 3, 4, and so on, all the way. So you get more complicated invariance, but the payoff is that you can build everything up from the small balls. So it really encodes locality in a strong way. Unitarity, by the way, is not part of this definition, but it could be added. Anyway, I'll just point out that there's a recent paper of Maxim Kontsevich and Graham, which talks about these axioms in the context of honest quantum field theories that are neither topological nor conformal. Okay, so let me just remind you very quickly of this general picture from field theory. Supposing that sigma, these sigmas are an n+1, I guess, dimensional field theory, which in a second will be a topological theory. Then we have the notion of a domain wall, that's the first picture, between two such theories. And if one or the other of the theories is the trivial theory, if you like, the tensor unit theory, then this is a boundary theory, but the boundary theories come in either left or right. And the left or the right is a little confusing. This is a right boundary theory because this is acting on the right of this, the same as it is with algebras and modules. In fact, I would use the terminology of bimodules and modules the same as I would in algebra to describe these domain walls and boundary theories. So what is this tensor product that in the algebra case recovered the vector space? Well, that you should think of as the dimensional reduction of this n+1 dimensional theory sigma along this interval with these two boundary theories. And that gives you an n-dimensional theory that doesn't sit on the boundary of anything. So we can also have defects, and defects can be supported on any kind of stratified nice set inside your manifold. Okay, so here's then the main definition, analogous to the definition of an algebra and its right module. And well, the first thing we called this was symmetry data for an n-dimensional field theory, on the background fields F. That seemed like a lot of words. So we settled on Quiche for some reason. The reason being is because as opposed to that sandwich, this is like an open face sandwich. But I'm afraid after we put out the paper, one of the friends, you can guess who, emailed Greg and said, you idiots, a quiche is not an open face sandwich, that's a tartine. All right. So anyway, what is this data? It's simply a topological field theory of dimension n+1, that's the sigma, together with a right module or a right boundary theory. Now in the algebra case, we said that it's the right regular module. That's what gets us the underlying vector space. Here, we have to do something to say that it's the right regular module. So in general, we might just have a right module. And that both of these are topological field theories. So these should both be topological. So the typical example, if you have a finite group, the usual kind of symmetry, then this theory in dimension n+1 is the pure gauge theory for that group. So notice that we usually say that if you have a G symmetry, you couple to a background G gauge field, or in this case, a G covering space. But this theory sigma is the quantum theory where we've summed over those. Okay, so here I'm not going to dwell on this, just to say that there is, as I said, a well-developed theory of topological field theories and fully local ones. And inside that, we could say what a regular module is in certain cases, what it means to say that rho is the regular boundary condition. And that's also sometimes called the Dirichlet boundary condition, the boundary theory. So the second part is to say, supposing we start with the sigma rho, that's our abstract symmetry or quiche. What does it mean to act on a quantum field theory F? So this F may or may not be, this one may or may not be topological. So typically it's not topological, right? And what it means is to give the same pair of data as before, we give a left module or a left boundary condition for this topological theory, and we give an isomorphism of this dimensional reduction, this sandwich, with our original theory. And that tells us that this is acting on our original theory. So that's the definition. I'll give you examples in a second. So as I say, they needn't be topological. This is not meant to be part of topological field theory. But what it is meant to do is separate out the topological part of the symmetry from the non-topological part. So typically this part, this F and that F tilde are not topological theories, but the sigma and the rho are. So anything happening in here, we can use the techniques and ideas and theorems of topological field theory to make calculations, as I'll show you. Well, this just says what you know, that symmetry persists under renormalization, group flow, etc. You can use, of course, that picture to try to draw dynamical conclusions, which I won't have time today to illustrate, maybe. Okay, so here's the first example, which is very close to the example of the algebra. This is quantum mechanics. So n is equal to 1. So this is a one-dimensional theory. And in this picture, you could think of this as really time. I mean, honestly, time, or perhaps with rotated imaginary time. And the sigma, so this is meant to be a quantum mechanical system with a finite group G of symmetries. So this is then the two-dimensional finite gauge theory. And this is the boundary theory you get by asking that you trivialize the bundle on the boundary. That's the usual kind of condition that you would give. And if you trivialize the bundle on the boundary, you're going to recover the original theory without the symmetry. So here I've listed maybe a little bit too much, some facts about that theory. But the basic things that give you the theory, here we have the Hilbert space and the Hamiltonian. Here we have that same Hilbert space and Hamiltonian, but we remember the G action. So it's just like the algebra case where we remember the module structure over the group algebra. Well, here's a more interesting example where we have a symmetry that I would call a BA symmetry. That's the name of this group. You would say it's a one-form asymmetry. And so this could happen in any dimension. And it might happen in a gauge theory where you have a gauge group H, I guess, where A is the subgroup of the center of H. It might happen that it has this symmetry. So for SU2, the center is plus or minus 1, and that would be the symmetry. So in that case, what is sigma? Well, sigma is the kind of one-up from this finite gauge theory. It's the gauge theory of these B fields that occurred in Jaume's talk that represent elements of H2 with coefficients in A. But again, it's the quantum theory where we've summed over them. And again, we have the notion of putting a base point, so to speak, this Dirichlet condition. And now here is, say, the SU2 gauge theory. And what goes here would be actually the SO3 gauge theory. So in this example, you see that the F tilde and the F look quite different, in fact.
About 10 minutes. Yeah.
All right, we'll get as far as we get. So let me now tell you again defects. And again, I'm telling you this in the most simple example, just to get, I hope, the idea across. But the paper has more interesting examples. So let's go back to the quantum mechanics case where n is 1. We have a Hilbert space and a Hamiltonian, a group, finite group acting on the Hilbert space, commuting with the Hamiltonian. And so this is the situation. This is this Dirichlet boundary, which is the right regular module for the group algebra if we evaluate on point. And ready. So we could first ask what are the point. So these are now, we're going to study point defects in this one-dimensional theory. So what are the point defects in this one-dimensional theory? Well, the way you compute it is you look at the link, the boundary of a tubular neighborhood, which here is just a zero-dimensional sphere. You evaluate your theory on that, and then you take a limit as that link shrinks. And so that's explained nicely in this paper of Kontsevich and Siegel. And what you get is some kind of limit of, well, the Hilbert space tensor its dual kind of operators on the Hilbert space. And this kind of limit gives you really quite singular operators, which is exactly what you expect in quantum mechanics. Anyway, I'm just focusing on the formal aspects. So we'll just think of them as operators on H and not worry about that. And so the idea is that we want to study these defects by transporting them under this isomorphism theta to this kind of sandwich picture. And the general defect will be then a defect supported on this interval, this manifold with boundary. So kind of stratified manifold. So one thing that can happen is we could have the, there's always a transparent defect, an identity, and we can put that on the middle, so to speak, and on the right, and just have the defect on the left. Well, you see now this is in the topological part of the theory, and so that's exactly going to be part of the symmetry, the defects that are in the topological part. So here the rule is, again, that you look at the link. Now the link, since we're on the boundary, is this interval with the boundary colored by this boundary theory. And now we don't have to take a limit. It's a topological theory, so it doesn't matter about taking a limit. And what you calculate is a vector space, and the vector space is just this group algebra. So that means the defects supported here, you can label them, so to speak, by elements of this group algebra. So in particular, you might label them by a group element. And those are the typical defects that you would say. When you have a G symmetry, you say in codimension 1, you have a submanifold labeled by an element of G. So that would be these defects living on this boundary. Of course, we could use any element of the algebra A. It needn't be invertible. Okay. Now we could look at a defect on the other side. Well, on the other side, that's not topological. We'd have to take the same limit. And in the end, what you get are operators on H that commute with the G action. Those are the ones that sit on this boundary. You could look at the ones in the middle. Those are again topological. And now the link is the circle. And it's well known in that two-dimensional topological finite gauge theory, what's attached to the circle is the center of the group algebra. So in particular, elements in the center of the group could label these, but you could have, again, more complicated labels, sum over conjugacy classes, for example. And the general one will be this kind of data. So of course, we have to, under this isomorphism, be able to reproduce the general operator here. And you can do that with this kind of data. You can work it out. Okay, so there's a composition law on defects. Here I've shown you what the composition on the topological ones. It's more complicated, of course, get into operator product expansions, that kind of law. But here you get an honest algebra from the topology, either the ones that are sitting on this boundary or the ones on the inside. On the inside, as we bring them together, we follow that motion, we would get this pair of pants. If we do it for these boundary defects, we would get this pair of chaps. And we could compute, well, so once you have this composition law, then there's also a transparent defect, the identity under that composition law. And then you have, of course, the notion of an invertible defect. So we could compute commutation relations. So for example, these point defects, well, it's very clear since these two are topological, we can move this one up and down the boundary, this one anywhere in the interior. We're not going to change the picture. And well, I told you this is a kind of central element in the group ring, so it commutes with this one. I told you these are operators that commute with the action of G, so they commute with both of these, etc. And you can see that these two commute is saying that, yeah, I told you already, that's in the center. So you can just visibly see that. And you could compute, if you label these by elements, you could just compute what happens when you commute, because you're computing inside this topological part. So even if there's a non-topological part, you can compute over there. So that's the kind of basic idea, just really talk is to advertise that picture of separating out the topology. Now, of course, we can do more. So here, going back to algebra, is the notion of a quotient, what you would call gauging. I shouldn't say you would call, what is typically called gauging a symmetry. It's really a quotient operation. And a quotient in the algebra context is given by what's called an augmentation. So an augmentation is an algebra homomorphism from A to the ground field. And for this group case, it's given by a character of G. One-dimensional representation gives you that augmentation. There are examples higher up, the kind of thing that lies behind, for example, in Jaume's talk, you would have higher versions of these kinds of augmentations. And the quotient, well, so I said when you put the regular module on the right, we get back the vector space underlying the left module. If we put this augmentation here, then what we get is the quotient. And you could do a little exercise with the group ring if you let it act, if G acts on a finite set and you make the vector space generated, you can easily see that you get the vector space on the quotient set. So you can see that you're getting quotients in that context. So in the field theory context, this is what might be called a Neumann boundary condition. But again, we can say in the field theory, topological field theory, we can say, what it means to have an augmentation. And in fact, these augmentations don't always exist. They don't always exist for algebras either. And that's really the obstruction to that is what the 't Hooft anomaly is saying that we couldn't take a quotient, we can't have this augmentation. So the quotient is just, you see, if I have an augmentation, we can put that on this right module instead of the Dirichlet. So instead of recovering the original theory F, we're really defining the quotient theory by that kind of picture. And once we have that, well, there are actually domain walls between these two kinds of topological boundaries. And so we get these domain walls between the theory and this quotient and the quotient back. And we could ask to compute the composition. That's one of these universal computations that you can make, as I said, in the field theory, in the topological field theory, without the particular theory that it's acting on. And there's a quotient operation. You can put that quotient operation on a defect. It was done in this paper, and that also plays well here. And well, I'm clearly out of time. Let me just end maybe with this slide, which is a particular computation of that quotient, of that composition of these two kind of Dirichlet to Neumann and Neumann to Dirichlet, or theory to quotient, quotient back to theory, defects. And here, there's a particular class of topological theories that are really quite topological, kind of homotopical, that were introduced way back in the 80s by Kontsevich and developed by Quinn in the early 90s and on and on since. And these are theories where you kind of sum over homotopy classes of maps into some topological space. And if you have finite symmetries, you can really get a full theory. And so finite gauge theories, the one-form symmetries, or the two groups, or more complicated things, they're all theories of this type. And the kinds of computations you make then become fairly simple computations in the homotopy theory of these spaces. So it looks very different than computing with the operators in the particular quantum field theory that it might act on, but of course it reproduces the same answer. So maybe that's a good place. And I'm sure I'm out of time.
Questions for Dan? Always look at Hiroshi first.
Pressure.
When you fuse delta and delta star together on the shrink for them.
This one.
Yeah.
Well, it depends on, of course, what topological field theory. So there are different formulas depending. In this kind of homotopy case, what you end up, if you were mapping into X, you end up mapping into the base loop space of X. So if, for example, you were doing this kind of finite gerb theory, where those are some of the examples in that paper, then what you'd find is a gauge theory on the defect between them. The gauge theory would be coupled a little bit to what's outside, but well, in one application I was going to show you it kind of gets uncoupled. But anyway, there's a shift like that in this context. In 3 dimensions, if sigma is 3-dimensional, you're operating on 2-dimensional field theories, then you can bring to bear the theory of fusion categories. And in that context, there's a formula inside fusion categories that could compute this composition. So as I say, we could bring to bear what we know. It depends on how we're describing this topological field theory.
Any more questions?
So two questions. So first, just to confirm, if I understand correctly, when sigma is 2-dimensional, the category is basically category of, say, that A model. So that's the limit in category language, algebra language. Right?
You mean that's what the topological field theory attaches to a point?
Yeah, so then the second more probably interesting question is what happens with this homotopic version when sigma is 4-dimensional? What you're saying is fusion.
Well, let's see. I mean, you could take one of these spaces X and you could make a theory of any dimension. So I wasn't sure. Oh, you mean the thing I said last to Hiroshi about, so if we were in braided fusion categories, do I know? I don't think we did that computation, but I think that's a computation one could think about. Yeah.
Yeah, Jan. Here is a general question, curious, what is right now the definition of quantum field theory? I'm confused because there was a time when we said anything that's based on light actually is a quantum field theory. Maybe that's an incomplete definition, but do we have a complete definition of a local unitary probability quantum field theory now that takes all these structures into account? And if so, what is it?
Yes, I agree that the Whiteman definition is incomplete or doesn't cover all the cases of interest. This kind of definition, which is incomplete, would be for a Wick rotated theory and viewed on compact manifolds. And then the idea would be that suitably enhanced, you could recover, there's a theorem in the classical case when you're on Minkowski spacetime, you go to Euclidean spacetime. If you start with Euclidean theory, there's a theorem of Osterwalder and Schroeder that lets you go back. So that was actually the main point of this Kontsevich-Siegel paper, where they looked at a Riemannian metric and they said, well, we actually have a certain domain of complex metrics where that includes Riemannian metrics, but Lorentz metrics, if they exist, are on a kind of boundary, which is the same picture in the classical Whiteman, Euclidean, Yost, and all that picture. And so, so they prove a theorem that when you have the Lorentz metric, suitable global hyperbolicity, then you can recover the correlation functions. But the theory is nowhere near developed, and you would certainly want to add something about, as you go to short distance, that you have a kind of limit. There's a conformal field that is well posed at short distance, so that you can expect something good to happen at long distance. But all that kind of dynamical behavior is in its infancy, but it's a great question because it's a great direction to think about.
Well, we should probably stop so we have a little bit of our break left. Let's thank Dan again.